All right, so this is Maths 71. We're talking about two topics today. We're going to be working on some material covering the Pythagorean Theorem, which is review, and also special right triangles, which is also review. Technically, just about everything that we do in this course by design is supposed to be review of prerequisite material. To give you kind of a refresher on the topics that are going to be important for understanding the trigonometry that occurs in the parent course, our Math 373 course. So the first thing that we're talking about today, again, is the Pythagorean Theorem. The Pythagorean Theorem. Okay. Now, if you have forgotten what the Pythagorean Theorem is, we are talking about right triangles specifically. So in the Pythagorean Theorem, we have a right triangle, and a right triangle is a triangle that has a 90-degree angle as one of its angles. The two shorter sides of a right triangle are called the legs of that right triangle. And we, for the sake of the Pythagorean Theorem, we always label them A and B. The third side, the longest side, which is the side opposite this 90-degree angle, is called the hypotenuse, and we always reserve a C for the hypotenuse. It doesn't matter which of the two legs you call A or B, but it's important that you always call the hypotenuse C. Okay? Now the lengths of these three sides, if this is a right triangle, are related by this identity, or this equation. A squared plus B squared equals C squared. Identity is the wrong word to use there. It should just say equation. This thing is what we call the Pythagorean theorem, and it's useful to find one of the side lengths of a right triangle if you know the other two. So in the assignment that you're going to be doing for this week, you're going to be given 2 out of the 3 values of A, B, or C, and your job is to find the missing one. So I'm going to say find the missing side length. Now, oftentimes, if we're doing problems involving the Pythagorean Theorem, you may have a picture to look at. You may have a right triangle in front of you. 2 of the sides would be labeled, 1 is not, and then you find that missing side. On the handout, you're not going to see pictures of triangles there. Instead, you're going to see something like this. A equals 3, B equals 4, C equals blank. And we just understand A and B to be the legs of that right triangle and C to be the hypotenuse. Finding this missing side is a simple matter of just plugging in what we know into the Pythagorean theorem and solving for what we don't, algebraically. So the Pythagorean theorem would say, let me call this problem number 1. The Pythagorean theorem would say that A squared, which in this case looks like 3 squared, plus B squared, which looks like 4 squared, equals C squared, and since we don't know C, we continue calling it C until we can figure out what it is. All right, now we want to do some arithmetic. So 3 squared is 9, 4 squared is 16, and that's equal to C squared. 9 plus 16 is 25. And now this is where we would take a square root of both sides of our equation here to solve for the missing piece, solve for C. Now in algebra, you're taught that if you take square roots of both sides of an equation, on the side with the constant, you're supposed to put a plus or minus. So normally we would be writing C equals plus or minus 5 here. But I'm not writing plus or minus, and the reason for that is because in the context of this problem, a -5 doesn't make any sense. Remember, we're talking about side lengths of a triangle, and it only makes sense if those lengths are positive numbers. So we use +5 as an answer. This would be 5, okay? Let's do one more. Let's suppose we have A equals 5, and B is going to be the missing piece in this one. And then let's make C equal to 7. Okay, 5 and 7, and we're looking for b. It's important to remember that these three values, a, b, and c, are not just arbitrary lengths on the right triangle, but rather a and b are the legs, c is the hypotenuse. That's important because you need to make sure the correct numbers go into the correct part of the Pythagorean theorem. So I know a, it's 5 squared. I do not know b, so we just call it b. That gives me 5 squared plus b squared. That should equal c squared, or 7 squared. Notice the difference between the last problem and this one. In the last problem, both constants were on the left-hand side of the equation, whereas here, one constant is on the left side, one is on the right side. That means the solution to this we're going to find in a slightly different way. I'm going to work vertically for this one. So 5 squared is 25. B we don't know, so we continue calling it b squared. 7 squared, that would be 49. The goal, again, is to solve for b, so I would need to subtract 25 from both sides. What is 49 minus 25? Well, that would be 24. Okay, so now b is equal to the square root of 24. Now, 24 is not a perfect square. That's off the screen a little bit. 24 is not a perfect square, and so I'm not going to plug this into a calculator. This is actually critically important for this class and for calculus, which comes later. In the vast majority of examples, if you have a square root that doesn't come out to something nice, like the previous example, square root of 25 was just 5. If you plug the square root of 24 into a calculator, you get this never-ending decimal. We don't like approximation in this class, if we can get away with it. There are some cases where we do round numbers, but for the most part, we like to leave things in radical form. So if this is going to give me an ugly, irrational number, I'm going to leave this in rational form. But what I will do is simplify this radical. Now, we'll talk more about simplifying radicals most likely in a later support class. So I'm just going to write what this simplifies to. It simplifies to 2 root 6. If you don't know how to get this, you can leave it in the form of root 24 for now, but it is going to become important that you know how to simplify radicals for the parent course. So 2 root 6, that would be the answer to this. Not whatever decimal this is equal to, just 2 root 6. Okay? So that's a little bit on the Pythagorean theorem. One more thing regarding the Pythagorean theorem that we want to determine, and that's its use in problems that don't seem to initially be about triangles. Let's suppose I have a rectangle like this. And let's suppose this rectangle is 10 inches by 12 inches. And I want to find the length of the diagonal. This is what we call the diagonal right here. Yeah, right? So even though we started with a rectangle, when I put the diagonal into this rectangle, it creates a couple of right triangles. And the diagonal of this rectangle I can see is the hypotenuse of this right triangle. And so a problem about a rectangle turns into a problem about a right triangle, in which I would use the Pythagorean theorem. So according to the Pythagorean theorem, a squared plus b squared, in this case 10 squared plus 12 squared, is equal to c squared. That's 100. That's 144, which equals c squared. Adding those together, 244 equals c squared. And then c is the square root of 244. And yeah, I can simplify that. I think I'm actually just going to leave it at this in this case. Now, in a separate problem, if this rectangle represented something specific, I believe on your handout, you're asked to find the length of the diagonal for a rectangular TV screen. that's whenever you see like the dimensions of a TV screen, they usually say this is a 65-inch TV or something like that. What they're measuring is the diagonal. They're not measuring the length of the width. It's the diagonal. And oftentimes, if it doesn't come out to a nice round number like 65 or 50 or whatever, you'll see decimals. So that might be one instance in an application problem where you may plug this into a calculator and get a decimal. But for my purposes, I want to leave this as a radical. And I'm not concerned with simplifying it for now. I just want to move on. All right. Now, very early in the course, by the time we get to the second section of our book in the parent course, we're going to start using something called special right triangles, but we're not going to derive any of that because the topic of special right triangles is something that you learn about in geometry, and geometry is a prerequisite for our parent course. What are special right triangles? Well, we know right triangles are triangles that have a right angle in them, but if this is a triangle, all three angles have to add up to 180 degrees. That's a basic fact for triangles, which means if this is 90 degrees, then the remaining two sides have to also add up to 90. And there's a number of ways that could happen. This could be 10 degrees and that could be 80 degrees. This could be 40 degrees and that could be 50 degrees. In a couple of particular cases, the triangles that result, for example, if this is a 45-degree angle and this is a 45-degree angle, this particular triangle is of special interest for reasons we're going to look at. We call this a 45, 45, 90 triangle because that's what the angles are. Another triangle of interest, special right triangle, is if we have a 30-degree angle and a 60-degree angle. Notice those also add up to 90. We call that a 30, 60, 90 triangle. Now, the reason we like special right triangles is related to what we just did with the Pythagorean theorem. So remember, with the Pythagorean theorem, we were using the theorem to find one missing side of a right triangle if we knew the other two sides. The benefit of special right triangles, as we're going to see in a moment, is that it's possible in a special right triangle, if you know what type it is, 45, 45, 90, or 30, 60, 90, to only need one side of that right triangle and then be able to determine the other two sides. You can't do that with the Pythagorean theorem in the case of a general right triangle, but you can with special right triangles. So let's investigate this for a moment. If I have a 45, 45, 90 triangle, it's 45, 45, 90. We're going to be using some results from geometry. We're not going to go and prove them because that's too much work to do in this class. We're going to just assume some important results. One thing we know about triangles is that if two angles are equal to each other, 45 and 45 in this case, then this is an isosceles triangle. Isosceles means two of the sides have the same length, and in particular, it would be these two sides, these two legs. So those little hash marks mean that those have the same length. So what we're going to do is say, let's let one of the legs of this right triangle be x. We don't know what x is. It can be anything in a particular problem, but to keep things general, we'll say x. Because this is isosceles and these legs have the same length, this would also equal x. Now, because I have 2 out of the 3 sides, I can apply the Pythagorean theorem to this. I'm going to think of the hypotenuse as c for a moment, and a and b are both equal to x. So according to my Pythagorean theorem, a squared plus b squared, in this case, looks like x squared plus x squared, and that will equal c squared. Okay? But these are like terms, so I can combine them. 2x squared equals c squared. Taking square roots of both sides shows me that c is equal to, well, when I take the square root, I have to take the square root of each factor independently. Square root of 2 literally just looks like root 2. Square root of x squared, remember we're keeping it positive, would just be x. That right away tells me the length of my hypotenuse as a function of x. So that means if I know one of the values, one of the legs of this 45, 45, 90 triangle. That becomes x, and I can plug that number into all of the x's to determine all of the sides. Okay? Now let's look at the 30, 60, 90 case. This is a tad more complicated, but in this case, we view the 30, 60, 90 triangle as half of an equilateral triangle. An equilateral triangle is a triangle where all three sides have the same length. Okay, so if this is 60 degrees, 60 degrees, 60 degrees, that produces what's called an equilateral triangle. All three sides have the same length. Now, if I were to drop a perpendicular from this vertex of the triangle down to the base of this triangle, from results that you would talk about in geometry, that bisects this base. What that means is it cuts it perfectly in half. Okay? So let's think about this for a moment. Not only does that cut the base in half, it also bisects this angle, giving me a 30-degree angle. So notice by chopping this equilateral triangle in half, one of these halves makes a 30, 60, 90 triangle. Now let's investigate this for a moment. So if I take this smallest side here, the side opposite the 30-degree angle would be the smallest, and in this case, that's what I'm going to be calling x. Okay? Then what can I say about the other two sides? Well, the hypotenuse of this right triangle is actually also one of the sides of the larger equilateral triangle. How does that relate to x? Well, x is exactly half of one of those side lengths of the equilateral triangle. So that means this length is half of this one, or said differently, this length should be double the size of this one, making it 2x. Now that I know 2 out of 3 sides in that special right triangle, I can determine this third side, the side that's opposite the 60-degree angle. Okay, so using my Pythagorean theorem, I'm going to call the angle, or the side here, B, because it's one of the legs of this right triangle here. A squared looks like x squared, plus b squared, we don't know what b is, equals c squared. This needs to be in parentheses. Okay, that gives me x squared plus b squared equals 4x squared. Subtracting an x squared for both sides gives me b squared equals 3x squared. And then taking square roots, b equals root 3x. That gives me the 3 sides of this special right triangle in terms of x, in terms of the smallest side. Okay? Let's look at how we could use this in the types of problems you're going to encounter in the handout. So we'll do one for a 45, 45, 90, one for a 30, 60, 90. Okay. So let our triangle be 45, 45, 90. Okay? And it's going to look similar to what we did in the case of the Pythagorean Theorem. I'm going to give you A, B, and C. And A and B will be the legs of our right triangle. And C will be the hypotenuse. Okay, so suppose I give you A equals 3. Okay, and B would also have to equal 3 because we're talking... Oh, sorry. I jumped the gun. We're going to assume we don't know that. Sorry. For these problems, I'm only giving you one of the 2 side lengths, not 2 of them. So from our 45, 45, 90 triangle, 45, 45, 90, either of the 2 legs I could call A, so that would be 3. Now, according to our 45, 45, 90 triangle, I labeled one of the legs x, the other leg would be x, and then the hypotenuse would be root 2x. So if I plug this 3 in for the x's here and here, I'll get b and c automatically. Plugging the 3 in here gives me 3. Remember, the two legs should have the same length in a 45, 45, 90 triangle. If I plug a 3 into this x, I get root 2 times 3, although we typically write that in the reverse order, 3 root 2. Notice I only needed one side length to find the other two. That's how we would work that through. All right, let's try a different one. Let our triangle be 30, 60, 90 this time. And now I need to be more specific about what A, B, and C are, because one of them has to be opposite the 30-degree angle, one has to be opposite 60, and so on. So let A, B, and C be the sides opposite the 30-degree, 60-degree, and 90-degree angle, respectively. Okay? Now what we want to do is, again, fill in the blanks. This time I'm going to say let A equal something. This time we don't know A. B, I'm going to say, is equal to 10, and C is equal to something. We're given one of those three sides. Okay? Now in this case, what's the relationship between the sides in a 30, 60, 90? So let's make this 30 degrees, 60 degrees, 90 degrees. We are told, well, first of all, here's our general right triangle. The side opposite the 30-degree angle we call x. The side opposite the 60-degree angle we found was root 3x, and then the hypotenuse we found was 2x. Which side do we know? We're told what side B is equal to, and B is root 3x. It's the side opposite the 60-degree angle according to how we described this thing. So that is what's equal to 10. Okay? Now, we need to figure out what x is. So this created a little equation that I can work with. Root 3x equals 10. I'd like to solve that. Divide both sides by root 3. X is equal to 10 over root 3. Now, you'll see in the parent class, we practice rationalizing denominators, and that's something we may also work on in this parent course if it seems like we need to do that. Because we're not talking about that specific topic right now, I'm going to just do the rationalizing and not explain the process in depth. We can reserve that for a different course. So this shows that x is equal to 10 root 3 over 3. That tells me what this is. Okay? Finally, what would 2x be? Well, if we know x, then 2x is 2 times 10 root 3 over 3, or 20 root 3 over 3. And now I have the remaining two sides. So I'll fill those in. 10 root 3 over 3, 20 root 3 over 3. And that's the idea behind what you're doing with special right triangles. That should give you everything you need to know to do this week's assignment.